Hello friends, so today we are going to solve questions from heat and thermodynamics. And these questions are from the year 2017. We are going to solve two questions and both questions are from advanced. And from 2018 also two questions, and these two questions are also from the advanced. So in totality we are going to solve four questions of advanced. So the first question, it was asked in the year 2017, and it states that an ideal gas is undergoing a cyclic thermodynamic process in different ways as shown in the corresponding PV diagrams in the column 3 of the table. Consider only the path state 1 to 2, state 2. W denotes the corresponding work done on the system. The equations and the plot in the table have standard notations and used in thermodynamic processes. If gamma is the ratio of the heat capacities at constant pressure and constant volume, the number of moles in the gas is n. So basically we are given that we are having these four graphs and we have to consider only the process between 1 and 2, and these are at various position in this PV diagram. So based on this we are having two questions in part A and there is part B. Okay. So first of all, basically it is asking that the column 1 we are given the various work done associated, and in column 2 we are giving various processes. So we have to match these processes along with their, you can say, the equations, work done equations. So first of all, let us start with our first equation, and first equation is our 1 upon gamma. Okay, so we are given that first equation is work done from 1 to 2 is given as 1 upon gamma minus 1 times P2 V2 minus P1 V1. So this is the work done first equation. Okay. And we have to find out which of the processes it is going to match. Okay. And for that we can use that our okay. So let us start with our, I think, much more easier if we start with the known graphs. Known graph is that for this P we know that our pressure is constant, and for our this S we know it is basically our volume is constant. Okay. So for this we are very much clear. Okay. So first of all, let us start with our this first process is given as our isothermal. So we are going to start with the isothermal and then we can do the reverse part. Okay, so I think that will be much more convenient. So we start with our processes, and first process is our isothermal. Okay, and for isothermal, we know that our temperature is constant. Our temperature is constant, and the standard equation for our ideal gas is our PV is equal to nRT. And from here we can write that P will be equal to nRT divided by V, and our work done and we can call this as our PdV, integration between the two volumes V1 and V2. P we already know, we substitute it and we get this as our integration V1 to V2, and this is our nRT V, and this is our dV. Okay, therefore we can take our nRT as constant, so sorry, outside the integration because it is constant, and we get this as dV upon V, so its integration will be equal to natural log of V, and this is our V1 to V2. So we get from here our nRT will be equal to natural log of V2 divided by V1. Okay. So it means work done for the isothermal process is governed by our okay, in this case we have to find out the work done on the system, okay, or we can say by the system. So therefore this will be negative in nature. So we can say that our work done on the system, and this is our by the system will be work done by the system. So this comes as our minus nRT natural log of V2 upon V1. So from here we get that for our third option, first option we have our option number 4 is correct. Okay. So we can say first matches with fourth. First matches with our fourth. And graphical we can just discuss later on also, it's not a big issue. The main is calculation of the work done. Second process is our isochoric process. So we have our isochoric, and isochoric we know that our volume is constant, and volume is constant, so for that we already know that our work done is equal to 0. Okay. So for volume is constant, we can say that our work done will be equal to 0, and we get the second matches with our third. Okay. So we can say our second matches with our third. Next process is our isobaric. And under isobaric we have our pressure is constant, and pressure is constant, therefore we can say work done by the system will be over PdV, which comes as P V2 minus V1, and that will be our negative of our on the system. So we can write this as our P V1 minus V2. So we have our isobaric, and this isobaric is our V1 minus V2. So we have second. So third is going to give us second. And finally we are having our adiabatic process. So obviously only one is left is our first. So we can just prove it also. So we come to our adiabatic process, and in adiabatic process we know that our delta Q is equal to 0. So from our first law of thermodynamics we can say our delta of U will be equal to our work done on the system, and we know our delta for U is our N, C of V, and delta T. And we can you can say write C of V, this will be our work done on the system, and we can write this as our work done on the system. This comes as our N, and C of V can be written in terms of gamma, so that will be R upon gamma minus 1, and we have this as delta of T. Okay. And by using our, let me write this 1 upon gamma minus 1, and this comes as NR, this will be T2 minus NR T1. So from the first law, sorry not, but from the ideal gas, this will be our P2 V2, and this will be our P1 V1. Therefore we get on the system will be 1 upon gamma minus 1, and this comes as our P2 V2 minus P1 V1. So we get that the fourth will be our first. So you can say our fourth matches with our first. Okay. And so therefore you can say that okay, it is having 3 A, B and C. Sorry, I missed out. Okay. And we found out the work done, and so from here we can say that our, it is asking for the combination, so we are going to get this as our third, we have second with fourth, second is with third, so the option number third with second, third with second. Okay, so we are going to have this option B is correct. Okay. And we come to our part B, which states which of the following option is the only correct representative of the process in which delta U is equal to delta Q minus PdV. Okay. So in this case, we can say that our delta Q will be represented by our second, third, and second matches with third, and it is going to match with our P. Okay, so we are going to have second, third, and P will be our option B is the correct one. And then we come to our determination of speed of sound in the ideal gas. Okay, so we can just calculate that. We know that our speed is our so we have to find out the speed. So in this case, we have to find out the speed. Okay, for speed we have our one second. So for the speed, we are given that our gamma is equal to C of P upon C of V, and this is our with respect to our adiabatic process, and for that we calculated our work done also. So we can say that our work done is upon P1 V1 P2 V2 and divided by gamma minus 1. And so I think I'm missing something. Okay, so we can just modify this equation and we can write this as P2 V2 minus P1 V1 upon gamma minus 1. Okay, and so for this we can, because there is only doubt upon two things, that either it will be a isothermal process or it will be the adiabatic process. Okay, and the difference lies between the slope of that. Okay, so we can say that with the help of Laplace correction, you can say using Laplace correction, the speed of sound in an ideal gas is adiabatic. Therefore, we have our option, that is our B is the correct one. Option B is correct. So next question. It states that it was also asked in the 2017 advance, and it states that a human body has a surface area of approximately 1 meter square. The normal body temperature is 10 Kelvin above the surrounding room temperature T0. Take the room temperature to be T0 300 Kelvin. For T0 is equal to 300 Kelvin, and the value of the Boltzmann constant time T raised to power 4 is 460 watt per meter square, where this sigma is our Stefan Boltzmann constant, and which of the following statements is or are correct. So here let us write the things which are given to us. First of all, we are given that the area of the body, surface area of the body, and let us suppose that A is given as 1 meter square. We are given the room temperature, room temperature is our T0, which is 300 Kelvin, and we have a body temperature, and it states that the body temperature is 10 degree above the room temperature. So that will be our 10 plus T0. Therefore, we get the body temperature T will be equal to 310 Kelvin. And rest are standard format, so need not to find out. So let's start with option A. It states that if the body temperature rises significantly, then the peak of the spectrum of electromagnetic radiation emitted by the body would shift to a longer wavelength. So we have to find out the relationship between, or we can say we know the relationship between the maximum wavelength as well as the temperature, and that is our Wien's displacement law. So we start with our option A, and for option A we say that as per our Wien's displacement law, we know that the product of maximum wavelength and temperature is equal to constant, which constant is represented as B. Therefore, from here we can write that our lambda max will be equal to B upon T. Okay. And in the question it states that if the body temperature increases significantly, so body temperature is our 300 Kelvin. So it means if the temperature of the body is greater than this 300 Kelvin. Okay. So from here we can say that our lambda max is inversely proportional to our temperature T. Okay. So which basically means that as this temperature increases, the lambda is going to decrease. You can say as temperature T increases, lambda max decreases, and this decrease in lambda max, we can say that the peak wavelength shifts to shorter wavelength. Therefore, we can say that our peak wavelength shifts to shorter wavelengths. And in the question that is given, it shifts to a longer wavelength. So option A is incorrect. Option A is incorrect. And we come to the option B, which states that if the surrounding temperature reduces by a small amount, delta T naught, which is much lesser than T naught, then to maintain the same body temperature, the same living human being needs to radiate, you can say this delta W is about 4 rho T naught Q delta T naught more energy per unit time. So it means if the temperature reduces, we have to find out how the body radiation is going to change. And for that, we are going to use our Stefan Boltzmann law. So we have our option B, and for that we are going to use Stefan Boltzmann law. Stefan Boltzmann law, and this law states that our this power radiated will be equal to, you can see our P net is equal to Boltzmann constant area and the difference between the temperature, that is our T raised to power 4 minus T naught raised to power 4. And we already know this area as sigma A product, everything is given. Therefore, we can write that our P net will be equal to, this comes as our area is given to us as 1. So we have this as 310 raised to power 4 minus 300 raised to power 4. Now it states that the temperature of the surrounding decreases. So we can say if surrounding temperature decreases, let us suppose new temperature is our T naught prime, initial temperature was T naught, and it reduces by the amount delta T. Therefore, our new power radiated, new net power radiated, that is P net prime, will be equal to, this will be our, this will be same, that is 310 raised to power 4 minus of, and this comes as T naught minus delta T whole raised to power 4. And we can say that the additional power radiated irradiated will be the difference between the two powers, that is, suppose our delta P will be equal to our, this will be our P net prime minus P net, and we substitute both, we get this as our delta P, and we are going to have this Boltzmann constant as common, and this will be coming as our 310 raised to power 4 minus T naught minus delta T whole raised to power 4 minus, and P net was our 310 raised to power 4 minus, let's keep T naught as T naught. And so from here this will be coming as minus and this will be coming as plus. So 310 cancels out, and we get this will be equal to over delta P is equal to sigma, and we have our minus minus plus, that is T naught 4 minus T naught minus delta T whole raised to power 4. Now we can use this binomial expansion, and under the condition that is given to us that our delta T is very much less than our T naught. Therefore we can write that this particular function we can take T naught as common. So let me solve it separately. So this will be T naught minus delta T whole raised to power 4. So we get this as our T naught 4 will be our common 1 minus delta T upon T naught whole raised to power 4, and this can be approximately written as delta T naught 4 1 minus 4 delta T upon T naught. Okay. And if you multiply by delta this T naught inside, we get this will be equal to over T naught minus this comes as 4 T naught 3 multiplied by delta T. Okay. So we substitute it, we get our delta of P will be equal to Boltzmann constant, and this comes as our, this is T naught power 4, T naught 4 minus this will be T naught 4, and this will be plus our 4 T naught cube delta T. T naught 4 cancels out, and we get that the net will be equal to 4, and we have this as T naught 3 delta T. So it means our option B is correct. Okay, it is written as delta W, so we can just substitute it by delta W. Okay. So this is same as our delta W. So we can say our option B is correct. Now we come to the option C. It states that the amount of energy radiated by the body is close to 60 joules. Now we have to find out simply our energy. Okay. So option C, and we already know that our net energy radiated per unit volume, which we also call as a power, net energy radiated per unit volume, we have already done that P net is equal to A, and this comes as our T raised to power 4 minus T naught raised to power 4. Okay. And it is said that we have to calculate it in 1 second. So we can say energy radiated in 1 second energy irradiated in 1 second, and that will be nothing but a P net. And area is given to us as 1 meter square. So we can just write it. We get this as P net will be equal to Boltzmann constant, temperature is 310 raised to power 4 minus 300 raised to power 4, and Boltzmann constant we also know is our 5.6. One second. Okay, Boltzmann constant is not given, but it's a standard value. We can also find out, because we are given that the product of T naught Boltzmann constant T naught 4 is 460. Okay, so we can just find out it. So we can say that our T naught is equal to 460. So this comes as our 460, and T naught is our 300 whole raised to power 4, and this will be coming equal to as 5.679 and 10 is power minus 8. Okay, so we substitute it. So we get this as 5.679 into 10 is power minus 8, and we have this as our 310 raised to power 4 and 300 raised to power 4. So we get this P net will be approximately equal to 61.14 watts, and energy in 1 second in 1 second will be equal to over E is equal to P net multiplied by 1, which gives us 61.14 watts, and approximately we can see it is 60 joules, not watts. Joules. So we can say option C is correct. And we come to option D, and option D states that reducing the exposed surface area of the body, that is by curling up, allows human to maintain the same body temperature while reducing the energy lost by radiation. Okay. And this is also based on directly the formula itself. Okay. So you can see our option D. And moreover, this is also a general concept that whenever we reduce our surface area, the net power radiated by the any body is reduced. So this is sigma A, and we have this as T raised to power 4 minus T naught raised to power 4. So from here we can say that our P net is directly proportional to the area. So if area reduces, the P net also reduces. So option D is also correct. So option D is also correct. Next question. It was asked in the year 2018 in advance, and it states that two conducting cylinders of equal length but different radii are connected in series between two heat baths kept at temperature T1 300 Kelvin and T2 100 Kelvin as shown in the figure. The radius of the bigger cylinder is twice that of the smaller one, and the thermal conductivities of the material of the small and the larger cylinder are K1 and K2 respectively. If the temperature at the junction of the two cylinders in the steady state is 200 Kelvin, then the ratio of K1 and K2 is. So basically we are given two baths. One is at temperature T1, which is given as 300 Kelvin. Other bath is our T2, which is given as our 100 Kelvin. In between we have two different materials of conductivity K1 and K2. The length of both is same. Okay. And so it is also given that across the junction is somewhere here. It is at steady state, it is given as 200 Kelvin. Okay. And the radius ratio is twice. Okay. So obviously the heat is going to flow from our 300 this T1, and it will be flowing in this direction to our T2. And because T2 is a hot, or T1 is our hot and T2 is our cold bath. So let us consider that the radius of our smaller cylinder is R, radius of smaller cylinder is suppose R. So radius of our larger cylinder, radius of larger cylinder, let us suppose that is our capital R, which will be equal to twice of small r. And the temperature of the junction is, let us suppose, given as our Tj, which is our 200 Kelvin. So the heat, you can say, is going to flow only because of the conduction. It is not mentioned in the question, but we are going to presume that there will be only loss of heat because of the conduction. Okay. So for that we can use Fourier law of heat conduction. Fourier's law of heat conduction, and that states that heat flow per unit time, heat flow per unit time, that is our Q, will be equal to K area delta T and L, which is our length. K is the thermal conductivity, A is the cross sectional area, and delta T is our temperature difference. Okay. And our area, we can say, is our pi r square. Okay. So we have our two cylinders. So we can write our, for first cylinder, that is A1, is our pi r1 square, and for bigger one we are going to have A2, that will be our pi 2 r1 square, giving us 4 pi r1 square. So we got the area of this, and the length is same for the cylinder. So we have the heat flow. We are going to consider two cases. First case is the heat is flowing from T1 to Tj, and the second case we are going to consider that from our 200 to 100. Okay. So let us consider so we have our smaller cylinder is connected to our between 300 and 200, and larger is connected between our 200 and 100. Okay. So let us consider first of all for our smaller cylinder. And for smaller cylinder, we know that our T1 is our 300 and our junction is our 200 Kelvin. Therefore, we can say that our heat Q and its conductivity is given as K1, area is our A1, and we can write this as delta T1 divided by length is same. So we can write this is our K1, area is our pi r1 square, and delta T1 is our 300 minus 200 divided by L. So we get our Q1 will be equal to K1 pi r1 square 100 divided by L. And now we come to our larger cylinder. And that is our Tj is our 200 and our T2 is our 100. Therefore we can write that our Q2 is equal to, sorry about this background noise, so we get this as our K2 A2 delta T2 upon L, and we get this as our K2 A2 is our 4 pi r1 square, and this will be our 200 minus 100 will be also 100 times divided by L. And at the steady state, Q1 will be equal to Q2. Under steady state, Q1 will be equal to Q2. So from here we get K1 pi r1 square 100 upon L is equal to K2 4 pi r1 square 100 upon L, and this pi r square L 100, all these cancels out, and we are left with this as 4 times K2. Therefore we get K1 upon K2 is equal to 4. Okay. Next question. It was asked in the year 2018 advance and it states that 1 mole of monatomic ideal gas undergoes a cyclic process as shown in the figure. V is the volume, T is the temperature. Which of the statements below is or are true? So in this case, we are given a monatomic ideal gas. So we are going to write some formulae which are associated with ideal gas as well as with our monatomic, and 1 mole is given to us. And so we can say that for monatomic ideal gas, and that is our 1 mole, we can write that PV is equal to RT, and our internal energy U will be equal to, and 3 by 2 RT, or we can say that change internal energy will be equal to 3 by 2 R delta T. And we can also write that our C of V will be equal to 3 by 2 times R, and C of P is our C of V plus R, which comes as our 5 by 2 times R, and adiabatic ratio, adiabatic index is equal to our 5 by 3. So these are the some of the properties. And let us draw this process once again on the larger scale. So we have a temperature, volume, and volume. Okay. And the process are given to us. So this is our second, third, fourth, and this is our first. Okay. And okay, so let us call this as our A, B, C, and D. So for A, let us call this volume as our VA, temperature as our T1. Okay. And let me also write this is our process 2. Process 2 goes from A to B, and for B let us call this as volume as VB, temperature is still our T1. So from here we can at least say that our VB is greater than our VA. Okay, this was our process second. Now we come to the process 3. And process 3 starts from our B, and B we already know is our VB T1, and it goes to our C, and our C is, suppose volume is a VC, temperature is our T2. Okay. And it is a slightly curved, therefore from here we can at least say that our T2 is less than our T1. And now we come to the process 4. process 4, it starts from our C. C is our VC and our T2, and it ends at a D, and for D, let us suppose volume is our VD and temperature is our T2. So from here we can say that our VD is less than our VC, and then we come to the process 1. Process 1, and that process starts from D. D is our VD and temperature T2, and it ends at A, which is having a volume of VA and temperature is T1. And from here also we can say that our VD is greater than our VA. Yes. Okay. So from this process 2, our temperature is same. So we can say process 2 is our isothermal expansion because volume is increasing. Therefore we can say the process 2 is our isothermal expansion. Therefore delta T will be equal to 0 and volume is going to increase, so we can say our delta V is greater than 0. And for process 2, it is said that we have to check whether the heat is absorbed or not. Okay. So we are going to find out basically our using the first law and find out the work done. Therefore we can write, because delta T is equal to 0, so furthermore we can write that our delta U, which was our 3 by 2 R times delta T, this will be also equal to 0. And the work done by the gas let us call this as our W by, will be equal to integration P dV, and P we already know is our RT by V dV and its integration. And therefore we can write that our W by will be equal to this RT we can take as common, so this comes as natural log of our final volume upon initial volume. Okay. And our final volume for process 2 is our VB. Okay. So we can write this as VB upon VA. And we know that our VB is greater than our VA, therefore we can say that our work done by the gas will be positive, greater than 0. Now we can use our first law of thermodynamics, that is our delta of Q is equal to delta U plus work done by the gas. Delta U is 0 and work done by the gas is positive, so this is also greater than 0. Thus we can draw a conclusion that the gas absorbs heat. Gas absorbs heat. Therefore, option B is correct. Option B is correct. Okay. Now we come to our next is our heat released. So process 4, and process 4 is our isothermal compression, because here also temperature is same. So we come to the process 4. Process 4 is our isothermal compression. And once again, delta T is equal to 0, and it is compression, so our delta V is less than 0. Okay. And once again, same equation, that the work done by the gas will be equal to our RT, natural log of our final volume, our initial volume. And in this case, process 4, our final volume is our D and our initial volume is our C. So this becomes VD upon VC. But we know that our VD is less than our VC. One second. Yeah, VD is less than our VC. Therefore, we can say that our W will be less than 0. So once again, our delta Q will be equal to delta U plus work done. Delta U is 0, so this comes as less than 0. Therefore, we can say that our gas releases heat. Gas releases heat. So if the gas releases heat, so we get option C is also correct. Option C is correct. This background cricket is very irritating. And now we come to the process 1, which states that process 1 is isochoric process. Okay. And process 1 is our, because there is change in volume as well as change in temperature. Okay. So, okay, let me drive it much more convenient thereby. So we have our process 1, and obviously there is change in volume, so we can say delta V is not equal to 0, and specifically we can say that our delta V is less than 0. Therefore, from here at least we can say not isochoric. It is not isochoric. And for our, you can say, we check whether it is isobaric or not, we can use our standard equation, which gives us that our PV is equal to nRT. Or from here we can say that our T is equal to PV upon R. And if pressure is constant, if it is constant, so you can say if P is constant, then we can write that our temperature is directly proportional to volume. Okay, but if under this condition temperature is directly proportional to volume, the graph should be a straight line. Okay? But for process 1, we can clearly see this graph is not a straight line. Okay? So from here we can say that TV path is straight line. Okay, let me write it here. So if P is constant, then we can say our temperature is proportional to volume, or we can say that our TV path should be straight line, which is not. So basically means that pressure is not constant. So if pressure is not constant, thus we can say that not isobaric. Not isobaric. Okay. So we have, so this is not isochoric and not isobaric. So option A is incorrect. Okay. And so process 1 is at least not isobaric, and we have to check process 3 now. Okay. And process 3, we can just same condition, because here also this graph is not a straight line. So this process 3 will be our not a isobaric. Okay. Therefore we can say that option D is also correct. So not isobaric, so we can say our option D is correct. Okay. I think this completes all the questions here. So this completes all the 4 questions. Thank you.